Hi, thank you, MC, Mr. Kivandra. Good morning, everyone. Assalamualaikum. Thank you for inviting me to chair this for this session. It is under biomaterial. You guys might wonder why I'm invited, because I'm also a research fellow in the Institute of Microengineering and Nanoelectronics and a visual artist. So we have 5 speakers today. So I will introduce you as we go along. But I will start this session with my own presentation. Let me share my screen. Okay. All right. This is a work that I'm doing, a research that I'm doing with my other research team, which is from the material packaging, because I'm part of the Electronic Packaging Research Society, which we specialize in printed circuit board, electronic packaging, and soldering material. So today's presentation, I'm going to share what we've done there in Institute Microengineering and Nanoelectronics in UKM, and it is called the Daun Pisang effect on banana leaves, as the general for banana is Musa genus, for biomimetic anti-wetting behavior. So my group consists of myself, Dr. Maria Abu Bakar, and Professor Azman Jalar from IMN and also Department of Applied Physics in UKM. All right, so let's look at a new understanding on surface morphology. So basically, we are material scientists, and we also look at the surface morphology and especially on surface finishes and coating for materials that we use for printed circuit board or any electronic packaging. So we're going to look at, okay, okay. So we're going to look at banana leaf. As you know, banana leaf is it has its anti-wetting characteristic. So what's intriguing about this banana leaf? If we look under the microscope, or we look under high magnification using FISM or IFM, infinite focus microscope, or electron scanning microscope, we can see that it consists of hierarchical structure. It has layers, you know. Yeah. So what we can find at this moment is that it has 3 layers. I'll show you later. And what's very unique about banana leaf, it has a microchanneling that act as guide to water droplets flow. Because if you compare to other anti-wetting materials that mimic the nature, let's say we call it lotus effect or the rose petal, you don't have this uniform microchannels. So so this is actually very intriguing for us to look it further into how we can actually study the surface morphology of banana leaves. So what we found is that it has whisker-like nanofiber in between this microchannel that grew from the bottom of this channel to ensure the flowing of water droplets to avoid stagnancy. So it's beautiful in a way that it's not just aesthetically beautiful, but functionally effective in directing the flow of water. So we call this phenomenon as controlling the droplet as Daun Pisang effect, based on a local name given to banana leaves. So so the highlight of this study is that we would like to introduce the Daun Pisang effect, consequence of this unique surface pattern of banana leaves. So that it is not only hydrophobic, meaning that it is not only anti-wetting, but it's also hierarchical structure. You will see later. We'll show you what we found under the microscope, under the high electronic scanning microscope. That also, not only that, it also contains a channel-like groove that can direct the flow to certain part of the leaves. So what we aspire from this study is that we want to shed light on how the switch of transitional state of wet and partially wet region, because before this, when you talk about anti-wetting, you talk about an established model from 1936 with an established assumption of hierarchical structure without considering the channel-like groove in daun pisang. But if we want to mimic daun pisang surface for its anti-wetting, so the model has to be modified a bit in a way that we might need to take consideration of this directional flow into the model, which is on the using calculation, so we can theorize it. We can also measure it empirically using CCD or other equipment. So for us, we don't see this mimicking of the surface of the pisang only for our applications, only for printed circuit boards. But as long as anything, it can be at a nano level, but it can also be at a micro scale level. So it's not just that, because but for us, since we are working on looking at surface finishes, looking at assembly of electronic packaging, so we try to see whether it can be used at our application, in our application. So if you look at the current technology of surface finishes, all are using coating, meaning you can have coating such as HSL. You can have HSL coating, you immerse the printed circuit board into tin or silver, or using organic preservative, inking using gold, hard gold, all depending on the, what you call that, on the functions and the needs of certain application. But what is the common disadvantage when you do coating? First is that you might get delamination. The coating might go through thermal shock, because when you have two different materials that is stuck together, that are laminate together, the possibility of its delamination might occur. And this and also depends on what you call as thermal shock. We might have problem in measuring the measurement of coating, because we don't want it to be too thick, because once it's too thick, then it won't be able to function well. We are also looking, it can also be easily oxidized. So what, and corrosion risk. So these are the things. So if you're looking at equipment, electronic device that can be used underwater, okay, that can be used really underwater, that is water resistant. So you're not looking at only coating, because coating, the worst thing about coating is that when it delaminates, it's going to create a very electronically unstable. It's going to be very active, the layers under the coating. So you would have a very strong or very severe corrosion risk, and pitting might occur. Then that can actually really affect your equipment. So let's look at the principle of wetting. It's not as straightforward as Wenzel or as Kessler-Baxter or even Young's model. These are based on assumption which was done in 1936. It was very long time ago, when we are not able to visualize, we're not able to study this surface. When you mimic nature underneath the microscope, we are not able to have a very high resolution, high magnification to look at what is the actual surface looks like. So the two parameters when you talk about wetting, so I'm going to look at non-ideal condition, non-ideal surface, which is, we call it rough surface. If it's ideal surface, then the model would use Young's model. That I think that is not usable in reality on application. So it does look into, if you look at surface, even though the surface in your naked eye look really smooth, but it's actually very rough, and it consists of hierarchical layers and layers of as you can see here, layers and layers of channels. Okay, so when we want to calculate on wetting, we're going to look at the contact angle, and we're also going to look at the contact angle hysteresis. But contradiction to earlier assumption that anti-wetting, or let me call it hydrophobicity, depends on high contact angle, lower contact angle also increase wetting. So that's kind of like throw all the assumption of the previous model of Wenzel, Kessler-Baxter or Young's model into something which is like, you might have a different calculation when you estimate theoretically, when you calculate using the mathematical equation, as opposed to the actual measurement of the contact angle. So we also need to consider the interaction of these liquids on the surface that can also cover several modes. So when you look at this theories of wetting, so we usually for rough non-ideal condition, non-ideal surface, we're going to use Wenzel or Cassie-Baxter model. But looking at the contact angle, if you look at the contact angle, if theta, say theta is 0, then you get perfect wetting. Perfect wetting meaning that it's totally adhesive. Your solid and liquid interaction is very strong, your liquid and liquid is weak. So, but we don't want perfect wetting. We are looking for an anti-wetting, meaning that we don't want the water to spend as little. We want the water to spend as little time as possible on the surface. So, if you're making an electronic equipment or devices, and you're going to use it for underwater, you can't have that luxury of the water. You can run off the water, meaning you can tilt it so that the water can just flow away. It will be exposed to water at a very long time. So we're looking into non-wetting. So we want a very strong non-wetting, meaning that the liquid and liquid cohesive, so we call it cohesive force. If it's liquid and liquid interaction is cohesive force, is very strong, and the theta angle is more than 180. And the solid and liquid, meaning the interaction between the liquid and the surface is weak. So then the water going to be like one nice ball. So it's 180. So that's a very strong liquid and liquid. So this is the current fundamental theories of wetting. But then if you want to mimic Daun Pisang, you can't actually use Cassie-Baxter or Wenzel, because Daun Pisang has another unique property that has a nanofiber in between the channel. So this nanofiber is actually the one that actually keep the water rolling. So the water won't just stay there, it will roll. We'll look at it later. So when we mimic nature, plant surface consists of very large diversity. It's very hierarchical. It consists of not just aesthetic, because I myself is a visual artist. I do sketching, I go to forests and do sketching and looking at all the surface and the beautiful colors of nature. But being a scientist also inside me trained me to look that beyond the aesthetic and to look at the function, and how aesthetic and how the beauty of nature is not just for beauty, but it's also for function. And this is where scientists come in, where we mimic, or we want to empiricize, or we want to measure it. Okay, it's 12 minutes. All right. So this is the images of superhydrophobic lotus leaf. As you can see, under the magnification, you can see a self-healing properties. So you can see that hierarchical structure. Okay, let's look at rose. Okay, rose petal, it has a rose petal effect. As you can see, there's a difference there, but it is quite similar, except for lotus leaf, you have a bigger space in between the structure, the morphologies. Whereas for hydrophobic, for rose petal, it's very tight. So that's why when water landed, or when water interact with the rose petal, when you tilt rose, okay, the water doesn't go down, whereas doesn't flow out. Whereas for lotus leaf, it's purely anti-wetting. So let's look at, I'm just gonna not talk about this. Let's look at our banana leaves. Since I'm in a banana conference, so I'm gonna bring banana leaves here. So look at the water drop after the rain. It's totally different. And this is under and magnification 10 times and 20 times under IFM, that shows like a groove. You know, it reminds me of sawah padi, the paddy field. It has channel, like it has rectangular structure. So if you look further inside, which is at micron level, you can see the banana leaf consists of this rectangular square stomata, and also this waxy nanofiber, which is very interesting because these fibers grow at the floor of the ridges. And what's the function of this? So we wondered, so how do this convex parallel fold that with the somata and fiber-like structure help or influence the directional flow? So when you look at, when we measure the water droplet on the surface of banana leaf, we have a contact angle 130. So remember, perfect wetting is more than 180. So for lotus leaf is 155. It is quite not as high as 180, but why is it the water does not stay on the water does not stay on the surface of banana leaf, right? So this is an illustration of how the water shape on lotus leaf, rose petal, and banana leaf. You can ask me later about this. Yeah, I'm just going to go really fast. So when you look at surface microstructure or morphology, you look at the lotus leaf has a very in-between space of this triangular helix. Rose petal has triangular helix, but it is tighter. But banana leaves, its anti-wetting comes from its structured ridges of rectangular form. Totally different from lotus leaf and rose petal, but give a very, very effective anti-wetting surface. Right, I think that's it for 15 minutes. This is what we have suggested, how a model for a banana leaf looks like. Okay, I'm open for question now. Thank you so much. Thank you. So I'm gonna start sharing. All right, any question from the floor? Or you can email me if we can, discuss further about this.
I have one question.
Yes, Prof.
So this I mean, this is why we use banana leaf anyway to
True that.
Because of this water. So when you are translating this design into packaging, how does it so it can be a macro packaging as well. It doesn't just have to be for microelectronic packaging, right?
Yeah, true. It can be on any anti-wetting surface because since with the nano size, so we're looking at that also.
So the potential for instance, food packaging.
Yes, definitely. So instead of using surface finishes where you coat, because you know the disadvantage of coating, it creates so much problem, right? Especially when you talk about chemical reaction, it might have delamination, you might have a cracking of the surface finish or coating. So if we can actually mimic the surface of the banana leaf at a micro level, looking at the hierarchical structure and also have the nanofiber. So we did, leading from this, we did an experiment trying to mimic it by using soft lithography using PDMS. We managed to get the nanostructure, and now we're figuring out how to actually plant that waxy nanofibers. So we're looking at 3D nano printing and see whether that can work for us. Yeah.
I'm actually saying, looking at application for solar panels, actually.
Yes, definitely. So that's something that we can consider.
Umbrella, from Jenny said, umbrella.
Umbrella, kan? Yeah.
Can I say something?
Yeah. Any question? I think Yaakob, Prof. Yaakob, raise your hand. Yes.
Yeah, well, actually, I just asked the same thing as what Prof. Yasmin did, actually, but looking at the application side, it's interesting how we can utilize the structure of banana. But I'm just thinking, how do we get it? How do we apply it in the commercial world? Because the thing I want to ask you is there a difference with the different varieties? They've got different hydrophobic characteristics. Does it go with different variety of bananas? And of course, the other one I mentioned earlier is how do we really get it down to the workable level? How do we get it down?
Yeah, at the fabrication level. So for our part, we're looking at 3D printing, and we're also looking at soft lithography, meaning that we are going to create mold for that. You see, because when you manufacture the circuit board, it already have a mold, but then the surface of the mold is flat. So if we can actually have a mold that have that surface, So we can produce that. So that would actually kind of disrupt. It's a disruptive technology for coating for surface finishes. So this is quite ambitious, but if we're looking at macro level, not just micro, maybe walls. Okay, maybe as you said, Prof. Jenny said, umbrella effect. Okay, we're looking at buildings. So that's something that is more doable if you have that kind of hierarchical structure with that nanofiber. So yeah, sorry.
I think interesting, since we have like 100 over sessions of banana, to see which kind of design is
right. I know, right.
has the best
model that we can take. So for us, we just take the banana leaf. Is it from I don't know about the specific scientific name, because as you say, it's 100 plus. So we're not from that expertise. Maybe we might want to work with someone from banana expert, that we look into it further and study different form of different surface morphology of all these banana leaves, and try to the first way we can do is to do a CCC, charge couple devising, by measuring the contact angle for the water droplet on each of these banana leaves. Okay. All right, thank you. So thank you for the question. So you have my email if you would like to look further into this, because now we're currently working with mathematician to work on trying to come out with a mathematical modeling for this. So we want to model it first before we proceed further.